Dear students, welcome back to our remaining portion of gravity dams. With that, lecture number 2, I think all of you got the full concept of stability analysis of gravity dams. After that, we are moving to the next lecture series. This is your lecture number 3. Here, we will discuss the remaining topics of gravity dams. To start with, let's discuss the modes of failure of gravity dams. There are 4 different types of modes of failure for a gravity dam. First one is overturning, second one is sliding, third one is compression or crushing, and the last one is tension. These are the 4 different types of modes of failure of a gravity dam. Let's discuss each of these modes of failure of gravity dams. First one is overturning. Overturning means it is the possibility of a gravity dam to rotate or overturn about its toe. So, in order to overturning occurs when resultant forces at any section cuts near the toe of the dam. I repeat, overturning may occur when resultant forces. This resultant forces means these are the resultant of various forces acting on a gravity dam. For the stability analysis, you know that we considered 3 different forces, that is self-weight of the dam, water pressure and uplift pressure, and the resultant of these 3 forces, if it is cutting near the toe of the dam, then overturning may occur. Again, going back to the concept of stability analysis, I explained you there. See, this is the total base width of a dam, and we are dividing the entire base width of the dam into B by 3, B by 3 and last B by 3. I told you there, this is your first B by 3, this is your second B by 3, that means middle third of the base, and this is your last third of the base. So, overturning occurs when the resultant forces at any section cuts near the toe of the dam. You know that if we consider the toe and heel of the dam, this is the toe portion and this is the heel portion. If the resultant of all the forces acting on a dam is near toe, this is resultant near toe, or at the last third of the base width, then overturning may occur. For no overturning condition, resultant should cut within the body of dam. Within the body of dam, I am detailing that sentence. Within the body of dam means the resultant should not be here. This is most dangerous condition. The resultant should be at the middle third of the base width. Then it's a condition of no overturning. So the basics is that for no overturning condition, the resultant should be within the middle third of the gravity dam. Now again continuing, the factor of safety against overturning can be calculated using this equation. I think all of you remembering this equation. This equation was used in the stability analysis check of gravity dam in our previous problems, and this factor of safety should be greater than 2. Going to the next modes of failure, second one is sliding. Dams will slide if horizontal forces are more than resisting forces. So horizontal forces means there is a possibility of horizontal force. Horizontal force means it is due to the retained water at upstream and downstream condition. You know that due to upstream retained water there will be horizontal force. Also due to downstream retained water also there will be horizontal force, and the dam will slide if this horizontal force are more than resisting force or the remaining force. There may be two type of sliding criteria: sliding due to frictional resistance and due to shear strength of joints. First one, the factor of safety against sliding. By considering the frictional resistance, the equation is mu into sigma v divided by sigma h. This equation was previously used in stability analysis problem, and that factor should be greater than 1. If you consider the factor of safety against shear friction factor, that is shear strength of joints you have to consider, then the equation changes to this format. This equation was also used in the stability criteria, where we took Q value as 14 kilogram per centimeter, and this factor of safety against shear friction factor should be greater than 3. This is the modes of failure against sliding. Third one is compression or crushing. You know that there is a possibility of compression or crushing at the bottom of gravity dam. At the bottom of gravity dam means there are two key points, that is toe and heel. This compression can be calculated using this stress equation, principal stress equation, that we already discussed in our stability analysis problem. While we move to the compression of heel, the equation changes. Instead of this positive, here it will be negative. Now the last modes of failure, fourth one is tension. You know that maximum vertical stress at heel, the equation is, instead of positive, here it is negative. If in this equation the value of E, again remembering you, E means it is the eccentricity. If eccentricity is greater than b by 6, then whole this equation will become negative. Stress at heel will be negative. Negative indicate it is tension. So if you are constructing any structure, no tension is permitted at the base of the dam or base of any structure like foundations. So for no tension condition, the value of E should be less than b by 6. So for no tension condition, E value should be less than b by 6. Again we are going to the preliminary statement, that is resultant should be in middle third of base width of the dam. Then only the tension criteria will satisfy. These are the 4 different modes of failure of gravity dam. In exam point of view, this modes of failure is very important. You have to consider, you have to take this topic very seriously. The next portion to be discussed in gravity dam topic is elementary profile of gravity dam. This is also very important portion in exam point of view. After this elementary profile of gravity dam, we will be studying practical profile of gravity dam. Then I will detail again what are the differences between elementary profile and gravity dam, elementary profile and practical profile of gravity dams. So when you consider the elementary profile of a gravity dam, there are 3 different types of forces that we are considering. First one is weight of the dam. Second one is water pressure only at upstream. We will not consider the water pressure at downstream for elementary profile in order to construct the elementary profile of a gravity dam. And the third force is uplift pressure. These are the three forces that we have to consider in order to study the elementary profile of gravity dam. Just giving you an introduction regarding the elementary profile of gravity dam. Actually, elementary profile means it is purely a theoretical concept. In practical point of view or in a site, we cannot adopt elementary profile for the construction of a gravity dam. Still, we will do certain analysis and certain equation using this elementary profile of gravity dam. Only for making such theoretical concept or theoretical equations, we will consider the elementary profile of gravity dam by accounting these three type of forces. Again, you have to listen very carefully. In water pressure, we will take only water pressure at the upstream. We will not consider water pressure at downstream for the elementary profile of gravity dam. This is the typical shape of elementary profile of a gravity dam. According to elementary profile of gravity dam, the shape of the dam is considered as a triangle. See, this is the triangular shape or the elementary profile of gravity dam, that is having a base width of small b and that is having a height capital H. This height capital H means it is the height of water or height of water that is retained at the upstream. So we will consider the weight of the dam, the horizontal water pressure due to this upstream head of water, and the third force, uplift pressure. Weight of the dam, first one weight of the dam, second one water pressure at upstream, third one is uplift pressure. These are the three forces considered for the elementary profile of gravity dams. So, an introduction to elementary profile. Elementary profile of gravity dam is of triangular shape with base width small b and height capital H. Here in this diagram, M1 and M2, two key points are marked, where M1 means it is at a distance of b by 3 and M2 means again it is at a distance of b by 3. Then from M2 to the top of the dam, again it is b by 3. So first b by 3, it is the middle b by 3 and it is the last b by 3. Now let's see each of the forces that we considered for the elementary profile of gravity dams. First force is weight of dam. You know that in the stability analysis and in the type of forces of gravity dams we studied, we can calculate the weight of the dam or the self weight of the dam using the equation area of the dam into unit weight of the material. See, here you know that the area of the dam is area of this triangle, that is half into b into s. That should be multiplied with the unit weight of the material. But there's a slight change. Instead of this unit weight of material, here the terms used are rho into W, where this small w is the unit weight of water and this rho is the specific gravity of the dam material. Very important point, you have to consider two important notations here, where small w is the unit weight of water and Rho is the specific gravity of the material. Material means using which material the dam is constructed. So the basic equation is sulfate of the dam equal to area into unit weight of the material. So instead of unit weight of material, we used specific gravity of the material into unit weight of water, because you know that by multiplying the specific gravity of any material into unit weight of water, you will get the density or unit weight of that particular material. I repeat, by multiplying the specific gravity of any material with unit weight of water, you will get the unit weight of material. So instead of unit weight of material, here we can use rho into W, where W is the unit weight of water and rho is the specific gravity of the material. And you know that, see, this is the sulfate of the dam denoted by W. As it is a triangular shape, its centroid will be acting at a distance of b by 3. So it will be acting b by 3 from base of the triangle of the elementary profile. Moving to the next force, that is water pressure at upstream. You know how to calculate the water pressure or the force due to water from stability analysis. The basic equation is W into H square divided by 2. See, it is the same equation, W into H square divided by 2, where H is the upstream water head and it will be acting at a height of, as it will be triangular variation, it will be acting at a height of h by 3 from the base of the elementary profile. And the third one is uplift pressure. See, this is the uplift pressure distribution diagram. You know that it is a case 1 of uplift pressure. For the case 1, there is only upstream water. There will not be tail water, there will not be drainage gallery. So here the ordinate will be unit weight of water into capital H. Here another additional term C is involved. So C indicate the coefficient of uplift pressure. So C is coefficient of uplift pressure. So along with the term WH, we will make use of another term, that is coefficient of uplift pressure. So this ordinate is C into W into H, and this is the direction of uplift pressure. So in order to find the uplift force, you know that you have to take the area of this uplift pressure distribution diagram. Area is half into, it's a triangular variation, so half into this distance is base into CWH. See the equation, uplift pressure U equal to half into B into CWH. And you know that it will be acting at B by 3 from base of the triangle. See, this is the uplift pressure and it will be acting at a distance of B by 3 from here. If you take the distance from here, it will be 2 by 3 of base width. These are the 3 different forces and force equations to be considered for the elementary profile of gravity dams. Next is the calculation of base width of elementary profile. In order to calculate the base width of elementary profile, 2 concepts are there using stress criteria, and the second one is by considering the sliding criteria. Now let's discuss the stress criteria. For the stress criteria, when the reservoir is empty, for no tension, resultant should act at M1. Let's read again. When reservoir is empty, let's see the elementary profile. When reservoir is empty, there will not be this upstream water height H, means P will be 0. Also, if reservoir is empty, this uplift pressure will also be 0. Then only remaining force is weight of the dam, which will be acting downward. This resultant will not also be there because there is only force W, and you know that this W will be acting at a distance of first B by 3, that is B by 3. That is what written here. When reservoir is empty, for no tension, the resultant should act at M1. But now see the next condition. When reservoir is full. Reservoir is full means there will be this capital H. So there will be horizontal water pressure, there will be uplift pressure also. So when reservoir is full, for no tension, the resultant should act at M2. Let's see what is the point M2. See, this is the point M2. I told you before, while we discussed the modes of failure in the tension criteria, I told you the resultant should be within the middle third of the gravity dam. So if you take the middle third, this M1 to M2 is the middle third. By taking the upper limit of middle third, that is M2 point. So our resultant should be within M2. That is the condition when reservoir is full. So for no tension criteria, the resultant should act at M2. Now we are going to take the moment of the forces about point M2, because the resultant should not exceed the point M2. So M2 is the key point. See, this is the step where we taken the moment. While taking the moment, don't mess up with our previous topic, that is stability analysis of gravity dams. Here, while taking the moment, clockwise moment is taken as positive, anti-clockwise moment is taken as negative. See, first is WH square by 2 into H by 3, which is the moment of the water pressure diagram or water pressure about the point M2. Let's see. See, this is WH square by 2 and it will be acting at a lever arm of H by 3 about M2, and the moment will be clockwise. For this elementary profile, clockwise moment is taken as positive. I think you are clear with this term. The next term is half into CWBH, means that is uplift pressure into B by 3. Let's see. See, this is the uplift pressure, and uplift pressure equal to half into B into CWH into, it will be acting at a distance of, this distance is B by 3, means we are taking moment about M2, and that moment also is clockwise. Since it is clockwise, the sign is given as negative. Now the next moment is negative, that is moment due to sulfate. You have the sulfate equation. See the figure. This is your sulfate, and sulfate will be acting at a distance of B by 3 about M2, and due to self-weight the moment is anti-clockwise. So the sign negative. And for equilibrium condition, sigma m should be equal to 0. That is why it is given as 0. Now multiplying this entire equation using a common term, 6 divided by w into s. You do the calculation. After multiplying with 6 divided by w into wh, this whole equation will change to this h square plus cb square minus b square rho equal to 0, where rho is the specific gravity of the dam material. By adjusting this equation, we will get b square into rho minus c equal to h square. We are going to calculate the base width of elementary profile. So from this equation, base width equal to h divided by root of rho minus c. If it is a condition of no uplift, let's put the c value equal to 0. Then equation will reduce to h divided by root of rho. This is base width of elementary profile based on stress criteria. Similarly, while taking the sliding criteria, for no sliding condition, horizontal force should be balanced by the frictional force. So horizontal force, what is the horizontal force for elementary profile? The only horizontal force is water pressure. So that water pressure P should be equal to frictional force. In order to find the frictional force, you have the basic equation, frictional coefficient into vertical forces. So this is capital P equal to, that is water pressure equal to mu into, now consider the vertical forces. Here the sign convention given us in such a condition, in such a way that upward force is positive, downward force is negative. So downward force is positive and upward force is negative. The same way that we put the sign convention for the stability analysis problem. But that was not the case here. Here we put clockwise as positive, anti-clockwise as negative. Here the downward force is taken as positive, upward force is taken as negative. So sigma of V means it is by considering self-weight and uplift pressure force. By readjusting this equation, again we are going to find base width. We will get the equation base width equal to h divided by mu into rho minus c. Again, for no uplift condition, this equation will reduce to base width equal to h divided by mu into rho. This is the end of the topic, elementary profile of gravity dam. It's a very important portion in exam point of view. So let me conclude the elementary profile. This is the elementary profile of gravity dam with triangular shape. These are the three different types of forces that we are considering, and this is the equation for various forces. The base width of elementary profile is calculated using stress criteria and sliding criteria. Now we are moving to the next portion, that is practical profile of gravity dams. Here I will tell you the difference between the practical profile of gravity dam and elementary profile of gravity dam. You know that the elementary profile of gravity dam is purely for theoretical concept, Actually, the elementary profile shape is not suitable for a gravity dam in practical point of view because of following reasons. See, we have to provide the roadway at top of every dam. Actually, in elementary profile, the top width is 0. Since it is a triangle, the top width is 0. So that is not applicable. Again, additional loads from top of road. There may be possibility of persons who are walking through the dam. Also, there may be possibility of movement of vehicles over the dam. So we have to consider those forces into account. Also, we have to provide freeboard. You know that freeboard is the distance between top water level at the upstream and the top of the dam. These three criteria were not given for elementary profile, so the elementary profile is not suitable for practical condition. By considering these three parameters, the elementary profile of gravity dam is revised like this. See, this is the elementary profile of a gravity dam. You can see that this is not a typical triangular shape. It's a complicated shape. And you have the various parameters like top width, and based on the top width you have this particular distance, that is a divided by 16. Remaining base width is equal to h divided by root of rho, where rho is the specific gravity of the material and small h is the upstream water head. After upstream water head, a freeboard is also provided here. Then the value of A, that is A means that is top width, that can be calculated using the equation top width equal to 14% of the height of water at the upstream. This particular distance can be calculated using the equation 2a into root of rho, and this height of gravity dam means from here to this point, that is calculated using equation 3.1 into a into root of rho, again where rho is the specific gravity of the material. This is the practical profile of gravity dam. Usually for freeboard, normally 1.5 times of small h is taken, where small hw is the height of wave. So there may be possibility of waves forming due to the action of wind in the upstream direction. This height of water waves are denoted by hw, and freeboard is taken as 1.5 times of hw. So in this figure, this freeboard can be 1.5 times of hw, where hw is the height of the water wave. So this is the basic difference between practical profile and elementary profile of gravity dams. Our next topic is high and low gravity dams. You know the basic equation for principal stress at toe of a gravity dam, and this is the equation. If you substitute instead of sigma v, if you consider according to elementary profile, you know that the vertical forces are uplift pressure force, and you have the uplift pressure force equation for elementary profile and self weight of the dam. So if you substitute sigma v, then b is the base width of the dam, and instead of e, if you substitute, e should not be greater than b by 6. So if you consider e equal to b by 6, that equation, this particular equation will changes to principal stress at toe equal to w into h into rho minus c plus 1. where W is the unit weight of water, capital H is the weight of water at upstream, rho is the specific gravity of the material, C is the uplift pressure coefficient. Okay, this calculation is explained in BC Punmya text. So if you refer or BC Punmya text, page number 208, page number in the sense PDF page number 208. See here, that calculation is explained. Principal stress equal to WH into rho minus C plus 1. This equation was explained there. Actually, no need of any derivation here. Just you want to understand this equation. And you know that the maximum value of stress, that means the maximum value of PV at tau, should not exceed allowable stress of the concrete. So instead of PV tau, the allowable stress of concrete may be substituted as F. And if you solve capital H, you will get the equation revised to capital H equal to F divided by W into rho minus C plus 1. Again, if there is no uplift, C will be 0, and this equation will reduce to H equal to F, where F is the allowable stress in concrete, F divided by W into rho plus 1. Now, based on this equation, we will divide dams into high and low gravity dams. See, if the height of the gravity dam, that is constructed in site, is less than this equation, then that dam is called a low gravity dam. If the height of the gravity dam that is constructed in a site is more than this value, then it is called as a high gravity dam. So this is the basic difference between low and high gravity dam based on this particular equation. Usually in exams, it's a common question: differentiate between high and low gravity dam. So this is the explanation for high and low gravity dams. Now we are going to the last portion of gravity dam. These are some typical terms that is being, or components that is being adopted or used in gravity dams: shaft, quay, water stops, grouting. These are the 4 terms that is being explained in our, or that is mentioned in our syllabus. Also galleries, you have to see what is the functions of a gallery, classification of gallery. Normally classification of gallery can be based on shape and based on location and purpose. Based on shape, it can be rectangular and oval shaped. Based on location and purpose, it is divided to foundation gallery, drainage gallery, gate gallery, grouting gallery, and inspection gallery. For this topic, gallery related topic, you can refer PN module text. And functions of shaft, quay, water stops, grouting is also there in PN module. These topics are also included in BC Punmya text, I think. If you refer PDF page number 214. See here, joints, quay, water cells. Here also different types of drainage galleries and its functions are explained. Just refer the textbook and prepare these topics for exams. So that's the end of our 4th module. gravity dams. Hope you all got the complete concept of gravity dam. In our upcoming lectures we will be detailing, or we will be going to our next module, that is fifth module, and that is arch dam. Thank you all.